So when you look at the definition here of electromagnetic spectrum, they do two terms, frequency. So frequency is how often the cycle happens within a certain period of time, all right? If you play an instrument, so let's use instruments. For example, I play the piano. If you play an instrument that has a really low sound, you're going to find a frequency that is way different than a high pitch, right? And so if you were to take a guitar string and pop it, how many times that thing bounces is going to affect whether it's a high note, it's bouncing really fast and lots going on, or a low note. And we have a much lower frequency there, okay? And so frequency is how often, and then it says or wave length. Well, that's the same thing. If I take a span of time and it moves really a lot of times in that span, then it's probably moving very quickly and it's maybe a really short wavelength. But if it only moves a couple times in that cycle, the frequency, then it's a really long wavelength, right? And so that's what you can think of as well, is the length of the wave itself or the number of times it happens. That's how they are going to arrange these different things, the electromagnetic. So you have a large family of waves. All electromagnetic waves travel at the same speed in a vacuum. So in a vacuum, they're all going to travel at 3 times 10 to the 8 meters per second. Radio waves are our longest waves and gamma waves are our shortest. And then we're going to talk about a whole bunch of waves in between those two. So waves with shorter wavelengths have higher frequencies. Waves with shorter wavelengths have greater energy for a given amplitude. Radio waves then are the least energetic. Gamma rays then are the most energetic. So radio waves are longer and less energetic. Gamma waves are shorter and more energetic, most energetic. So we are looking at the two ends of the spectrum when we talk radio waves compared to gamma waves. Okay, they are on the two ends of the spectrum. And they show you over to the side. You have very fast moving, you have very long, right? So you can see if you were to bounce a ball very quickly or if it were to drag very slowly. That's what we need to think of when you think of a wave. And so we have long wave radio. What is that used for? Anybody know what long wave radio? And then you see at the very top where we have gamma rays, all right? We have really high frequency, really short wavelength versus a much longer frequency down here. And then we're going to talk about all of this in between. All right. So that's just, as we say, spectrum. That's what we mean by spectrum. So you have a range going from way down here, very, very low frequency to way, way high frequency. And we're going to talk about all the things in between and what it's used for. All right. So types of these. The first one we're going to talk about is radio waves. Radio waves are produced by accelerating charges in a conductor or a conducting medium. So you've seen radio towers. As you drive around, the highest frequency radio waves are called microwaves. That should sound familiar. Obviously, we've all listened to the radio, so communication, television signals are all in the same. Obviously, we don't call them radios, but they're in the same set of waves. Radars, microwave ovens, which we probably all have in our homes. Wireless networks, astronomy, use radio telescopes. So these are all in the same group of waves. Infrared waves, these have less energy. They're lower frequency than the red light of the visible spectrum, all right? And so if you have ever seen a medical chart, so like, for example, one of the things that I do every year is called a thermography, and they use infrared waves to detect heat sources, all right? It's the same way as they would do to look at like a mammogram for a woman or something like that. It will detect, actually it's really good detection of cancer because cancer is warmer than most of your body. So cancer shows up very, very hot, very red when they do something like this. If you've ever seen night vision type technology, right? That's going to be infrared that they're doing, right? They're looking for a heat source that's going to show up as a different color on your night goggles than if it were during the day, right? If you've ever seen that type of imagery, this is where this is going to be used. So it's used in medical, it's used in satellites, fire detection systems, again, because your hotter sources are going to emit different waves that they can pick up on in a color spectrum. And like I said, night imaging, like night goggles, things like that. Police use it for search and rescue. It was just on the news, probably in the last couple weeks. A child got lost at a campground, and they were using night vision searching for it, and they saw the heat source, and they were able to find the child, right? And so that's what they're using there. They're using infrared waves. Visible light waves. We are all familiar with visible light waves because we use it every day with our eyeballs. All right. Newton did a lot with visible light rays. Newton was one of the first to separate visible light into what we know as the color spectrum and then put it back together. Prior to that, they thought that the spectrums that they would see were just reflections of other colors. Newton is the one that decided to use a prism to separate it, and then he used a prism to put it back together, and he realized white light is made up of visible spectrum of colors. And so this is obviously used anytime you use color. Anytime if you take a theater class and you study like the lighting of theater, or if you work with it anywhere else, they use a lot of shading and lighting in theater to enhance certain colors or to deflect certain colors. So visible light waves. And then they give you the band of those light waves, 4 times 10 to the 14th and 7.7 times 10 to the 14th. So it's a very small band that it's used, but millions of colors in that small band. Ultraviolet. These have more energy. We're going up the spectrum here. Ultraviolet waves, higher frequency than violet light of the visible spectrum. There are 3 bands of UV light, and I don't think I have this in your handout. UVA, this is used from anything from like skin problems, or if you've ever had any dental work and they put it through like a UV light. I mean, if you have your nails done, they use UV lights, right? It can harden stuff. When they do your little molds for your teeth, they'll put it in there so it'll harden faster, right? That's one of the UV lights. UVB, it's used in chemical testing for quality control, and then UVC, again, medical equipment. UVC is treatments for food and water, so sometimes purify and clean food and water, air purification as well. All ultraviolet waves. And the name tends to indicate higher frequency than the violet light of the visible spectrum, why it's called ultraviolet light, UV. This is one you have probably heard of. X-rays. X-rays are able to penetrate solid matter. Most solar and cosmic X-rays are absorbed by the atmosphere, but we also use X-rays. Clearly, probably everyone in here has had an X-ray. If you've been to the dentist, you've had an X-ray. If you've broken a bone, you've had an X-ray. Or if they think you broke a bone, you've had an X-ray, right? And they can see the bone and see what's wrong with it. Again, something that overexposure to can be harmful, right? If you've ever been to the dentist, what do they do before they stick that X-ray on you? They leave the room or either put on a big lead vest, right? And then they stick you in there to be exposed to the X-rays. But the difference is they are doing this every single day, right? And so they're doing it every single day. They're going to leave the room as opposed to you have it once a year, right? But what are the benefits of X-rays? Well, again, if you've ever broken a bone, it's kind of important that they know what to do with it, right? And so X-rays are one that we use probably all the time, that we are probably most familiar with. All right, gamma rays. We are not going to be as familiar with gamma rays because they are produced by high energy changes in subatomic particles. They can be very damaging to human tissue. We do use them though. They're hard to reproduce. So gamma rays are one of the hardest to actually reproduce, probably because of how high energy the frequency of them. They do inspect like metal surfaces where an X-ray would not be able to inspect a metal surface. Gamma rays could. And then some biology experimentation they've done. But if you think about if they are testing like the hull of a boat to see if there's cracks or something, some heavy metals, they can use gamma rays to detect weaknesses in it. Not necessarily see through it like an x-ray, but definitely detect a change in what's happening there. So, as usual, we have scientists, and you're going to see the same names because they were very curious creatures. Galileo tried to determine the speed of light using lanterns. It did not really work. So he had his assistant go like a mile and a half. I don't know how far away it was, actually. They gave it to me in kilometers, which doesn't convert in my brain. But he had a lantern. His assistant had a lantern. So he's uncovered the lantern, and as soon as his assistant saw the light from Galileo's lantern, he would uncover his, and Galileo timed the back and forth. His was not very accurate at all. As you can imagine, human error there. The guy's like, do I see a light? Oh, yep, there's the light. Reaction time, he was way off. But then we have Romer, who studied eclipses. So his idea was, if I know what time it's, because they've been predicting eclipses since early BC, way on, we've had eclipses. So if he knew when one was coming, he would use that to say, okay, how long does it take? You have to understand, too, that if we don't fully understand, Kepler has come into the play to know about elliptical, like we have some calculation errors that could happen. So then we get to Fizeau, French, by the way. He used a notch wheel and a mirror 5 miles away. He would actually spin the wheel and calculate how long it took to spin and how the light flickered and calculate it. And he was within 4% of the speed of light, which is pretty good considering he was like in the 1800s here that he's doing this, right? And then from his experiment, we have another, Foucault was another scientist who used conceptually similar to the same idea. He has like a mirror reflection, which is similar to what Fizeau did. But he was the first person to determine light in metric terms using terrestrial, right, methods of the Earth. 1862, which is pretty daggone good. Hertz. This name should sound familiar. We measure things in hertz. Made a device that could produce and receive radio waves. There we go, hertz, okay? All electromagnetic waves propagate with the same speed in a vacuum, which is 3 times 10 to the 8th. I think we talked about that earlier. This was a schematic of his crazy invention here. Here we have some induction coils. We have a receiver. We have a spark. We do not think about all that goes into when we turn on the radio, but alas, there's a lot more that goes to it than just pushing a button. And so Hertz, as we have so aptly named the measuring of these waves, was the first to produce and receive radio waves. When electromagnetic waves have their highest speed in a vacuum. Highest speed in a vacuum. And we're going to talk about mu and epsilon effect. We're going to do some math calculations of light tomorrow. We're talking about the fact that electromagnetic waves have their highest speed in a vacuum. So when you look at these two words here, you have the magnetic permeability. You see the mu, or that Greek letter there, that represents permeability. The measure of this is pretty much the response to like the magnetic field around it. You've heard the term permeable, probably, like how something can go through something. And then you have electric permittivity, that's epsilon, that's a lowercase epsilon. And this is the ability of something to like store energy. And these two things basically explain how something makes its way through. Remember, we said in a vacuum, it's going to move at a certain speed, which is that 3 times 10 to the 8th meters per second. That is the constant if we were in a vacuum. However, electromagnetic waves are affected by things around it. And so you have two things that affect it, the permeability and the permittivity of the medium being what it's going through, okay? And so you have this equation to calculate what does it look like then for it to go through something else other than a vacuum. How quickly is it going to move then? It's not going to move 3 times 10 to 8 meters per second outside of a vacuum. Some other things are going to affect it. So 1 over the square root of mu times epsilon. Most of the time, though, they're going to give it to you in a factor times the constant. Because basically you take the constant and you're going to multiply it by a factor, and that's how it's going to move, affected by that, whatever you have. And so if you remember that the constant is going to be the 3 times 10 to the 8th, then on a lot of these word problems, they're going to say, hey, the permeability is this times the mu sub naught, or the constant. And the permittivity is this times the epsilon. All right, and so then you're going to actually multiply them out, which is how our problem that you see, hopefully on your page, it says a beam of orange light travels through pure water at 20 degrees Celsius. Water at this temperature has an electric permittivity of 1.77 times epsilon of naught. That is part of your constant. And a magnetic permeability of 1 times mu sub naught for this color of light. What is the speed of light through water under these conditions? All right. So they've given us the epsilon and the mu, the 1.77, but you'll notice they're saying, hey, that's being multiplied by the constant piece of in a vacuum. And the 1 times the mu, also the constant piece of the vacuum. So we're going to plug it into the formula, and then we're going to pull out the constant piece of it. The formula says that the velocity through this specific medium, in this case, pure water at 20 degrees, looks like this. 1 over the square root of my mu, which is 1.00 mu sub naught, and my epsilon, which is 1.77 epsilon of naught. If you remember anything about radicals, you should remember that you can take, I'm not going to write it quite that big. You can take them if they are being multiplied and you can separate them out. That's 1 times 1.77. And that's the same thing if I then multiply this whole thing as the square root of mu sub naught epsilon of naught. Remember when you multiply radicals inside to inside? It'd be like saying the square root of 6 is the same thing as the square root of 2 times the square root of 3. I've just split it up. However, if you'll recall, one of the ways they defined the constant looked like this. That is also my constant in a vacuum. And so I can replace this whole piece with that number right there. I can take this number and just multiply it by my constant. So I can say 1 over 1 times 1.77, that's just that. And then replace this whole thing with my constant of 3 times 10 to the 8th. That is multiplying. Okay, so in your calculator, unless it happens to give it to you in scientific notation, you're going to get this big, huge number. Something like that. All right? I don't want you to give me that. I want you to give me scientific notation here. All right? And so with scientific notation, we're just going to count until it's between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8. I'm going to use 3 of those significant digits right there times 10 to the 8th. We are talking about velocity. All right, meters per second is what my velocity is in right here. So that's what it's going to be. first one is incandescence. Incandescence. You have probably heard of an incandescent light. If you've ever had any sort of critter that needed to be warmed, a heat lamp, right? That you would use for something like a, bearded dragon or something. They can't be under a certain temperature, right? And so those are going to be incandescent lights. A lot of them used to be. If you have ever replaced a light bulb and it's super hot, right? It's probably more on the incandescent side because we're releasing heat. But it's an object heated until it glows. They also give you, an example if you've ever worked with any sort of metal where you have to heat it up. You're going to notice that it glows when it gets to a certain temperature, right? That's how they brand cattle, right? They just heat it and it'll be glowing. All right, hotter bodies emit higher frequency radiation. The infrared waves become visible waves. All right, so that is incandescence. That is a type of light. You'll see this wavelength spectrum here. And so as we go through these, we'll talk about intensity. The next one is gas discharge tubes. These are sealed glass tubes with electrodes and gas sealed within them. They give you examples here of the different types of gases that will actually emit visible. Large potential difference produces current in the tube, and as the electrons move to lower energy levels, they emit light. So they're sealed, and as they slow down or move to lower energy levels, they emit light. Gas discharge tubes. Lasers, we've all heard of this one. They produce coherent light that combines multiple identical in-phase waveforms to produce a single energetic electromagnetic wave. Laser light is extremely intense. If you've ever gotten a little laser pointer, it'll actually say not to point it in your eye. I don't know who's doing that, but it can be intense light because it is honed in. They actually show you a little bit. They have like a flash tube, and then they funnel it down so that it's very pinpoint accuracy, which is why it's used for like laser pointers. That's why it's used in, objects. If you've ever been to a laser show, it seems as though the light's still there even once it's gone. Most of you probably don't know what it stands for, but you've heard of LEDs. LED light emitting diodes. They're made from semiconductors or semiconductor material. It emits light when a potential difference is established across them. They have low power requirements. They are very efficient. You probably have LEDs somewhere in your home, somewhere. A lot of closet lights that are activated by movement are LEDs. These string lights that people like to put up in their rooms, those are LEDs, right? Even a lot of your, even exterior lights are often LEDs. So they're very efficient. They don't produce heat. You can touch those. You'll notice that they're not warm, right? And so you have a semiconductor. So you actually have, in fact, if you've ever looked at a strip of LEDs, you'll see like a metal strip underneath it because they're going to use some type of conductor, right? Cold light. We're actually more familiar with this than we realize. If you've ever had a glow necklace or a glow bracelet or a glow stick, it does not get warm, right? But what do you have to do with a glow stick or a glow necklace or a glow bracelet before it will light up? You have to pop it, right? That is because cold light is produced from chemical reactions. So they have inside of those a tube and a tube. When you break it, you're breaking the inside tube so that the inside mixes with what's around it and it creates that chemical reaction. You'll also notice that after a day or so, it no longer is glowing, right? Because the reaction has come and gone. All of the substance is still there, but the chemical reaction has settled at that point. At first, it's all frantic, trying to figure out what's going on and, combine the way it wants to. And then, of course, my favorite, bioluminescence, is also a type of cold light, but this case is by living things. So if you've ever caught a firefly, they are not warm, right? Because they light up, right? That's a type of bioluminescence. Any questions on sources of light? Questions? Traveling in waves. When you think of waves, you probably think ocean, right? But a point light source. So if you have a point light source, it emits a spherical light wave. You probably know this intuitively if you have ever used a flashlight. All right. And so your flashlight comes from a point, and then what happens? You have a circle if you put it on the wall, right? And a lot of flashlights have an adjustable where you can actually adjust how large that radius is of the circle based on them moving that point closer or farther out, right? So point source emits spherical light waves. The sphere expands as light travels. A straight line wave surface is a plane wave. All right. So this is going to expand like a pebble in a pond. If you have something that is not a point, you're going to have what's called a plane wave, a plane wave. So then we get the term wave front. Wave front. All the identical points along a wave pulse or a curve connecting the crest of the outgoing waves. It's just called the wave front. Both of those represent types of wave fronts. It's all the points along that wave that you see. Kind of connects the points. And it's what you see, like I said, when you're using a flashlight, you're going to see that curvature and how that wave is coming out. They're going to be parallel to each other. So if it's a planar, you're going to see parallel forms. So for a point source, you're going to see the spherical. For plane waves, you're going to see wave fronts are planar and the light waves are parallel. And so you're going to see a curvature if it's a point. And if it's a plane, you can think of the word plane just from geometry. They're going to be parallel like this, not curved. All right. Yet another scientist. Christian Huygens postulated that every point on a wave front acts like a new source of small spherical waves called wavelets. A spherical wave front propagates as a spherical front, and a plane front propagates as a plane front. So he's just saying that his postulate said that you have these new waves that are coming off and coming off and coming off, and they will come off the same way. Like a wavelet's going to come off the same way that it was initially done. So the one coming from a spherical is going to come in a spherical form, and the one coming from a plane is going to come that way as well. And it's known as the Huygens-Fresnel principle. The Huygens-Fresnel principle. Just kind of a review of all the things we've talked about with the different types of waves. Light is the entire electromagnetic spectrum. So we think of light just as visible light, but light is the entire electromagnetic spectrum, all the way from the radio waves, which we talked about, transmit signals, microwaves, used for more than just your food, right? Guiding airports, cooking food, cell phone. X-rays and UV rays are both used in medical field. You'll also hear UV rays with the sun and with tanning, things like that. IR, that is also infrared. Infrared is IR to transmit signals. Electronic devices like your remotes will use infrared. All right, so just a summary of all of those.